here a little bit. I'm going to talk sort of about the macro picture. If we are able to go back to the moon and we are able to access volatiles, how would we use that to create new capability? So I want to start off by kind of reviewing how we got here. I like to break the history of the space program into three ages. The space race age, of course, was from the beginning to about the early 70s, where we were racing the Russians. We went to the moon, we came back, but at the same time, we developed a sense that there was practical value to space. We learned to make weather satellites, we learned how to do communication satellites, remote sensing from orbit. All those things were demonstrated in that early stage. The next phase was sort of a return to the von Braun architecture, which basically envisions a shuttle, a space station, a moon tug, and a Mars mission. And NASA always goes back to that architecture when it doesn't know what to do next. So we did the shuttle, we did the station. Now the question is, where are we going next? And in the von Braun architecture, it's to go back to the moon, building a moon tug, cislunar space, and then go on to Mars. But instead, we find ourselves in a debate, and that debate has come about by virtue of political instability and financial problems. So I call this the beyond LEO age. And the question is, where are we going beyond low Earth orbit? To do what? And what is the new value of going into space? So if this is such a great idea, what's the problem? The problem is space flight is difficult, and it is expensive, and it is barely possible. The fundamental problem is you've got this thing called the rocket equation, which Tsiolkovsky discovered over 100 years ago, which fundamentally means that a rocket is mostly fuel, and you're not able to get very much mass into low Earth orbit. So when you arrive in low Earth orbit, you have empty fuel tanks. And to go beyond that, you need to either bring a fully fueled stage with you or refuel in orbit. So fundamentally, because of this, you're fighting against this very deep gravity well that we live in. It's very, very difficult to send a payload into low Earth orbit and keep it there. It's not a trivial issue. You can't just roll these things out on a standard factory assembly line. The other problem is that the benefits of space flight are not intuitively obvious. We talk a lot about human destiny and colonization and the because it's their syndrome. And typically that's not a good argument to Congress. They don't like to approve things just on those kinds of nebulous rationale. So to put this another way, what is our ultimate goal in space? I think it is to be able to go anywhere, anytime with the capability we need to do any job we can imagine. Now we are light years from that kind of capability. But I think that what you want to do is to develop a strategic path that incrementally advances you toward that kind of capability. Right now, because we launch everything from the Earth, spacecraft are mass and power limited and therefore capability limited, and will always be that way as long as we remain restricted to what we can lift out of the Earth's gravity well. So what you really need to do is to be able to learn to use what you find in space to create new capability. And that's the real value of ISRU. That's the rationale for ISRU. Now, what is the value of space to our lives? In fact, it greatly impacts our lives every day in 1,000 ways. And in many ways that were not even envisioned at the beginning of the space age. We really depend on it for things like weather prediction, for strategic reconnaissance, for remote sensing, for communications. All of those things that we do now, we depend on for satellite assets, follow a very strict template because we can't really access those satellites once they're launched. If you have to custom design a satellite, launch it to the proper orbit, use it for a certain amount of time, and eventually abandon it because these things wear out, they become obsolete, they start to fail. So the current template of spaceflight is to custom build these specially designed mission-specific craft, launch them on expendable vehicles, operate for a set lifetime, and then abandon it. And then you go back to square one. Now what instead, if you could build, using small incremental blocks, bigger, larger distributed systems in space? You would launch from Earth only what you needed to launch from Earth. You would get bulk material and things like propellant and life support consumables from what you found in space. And you build and operate flexible and modular and extensible systems. Effectively, you are changing the paradigm of spaceflight. You're becoming less dependent on the logistical train from the Earth, and you're able to create more capability by using what you find. So one of the things we learned from shuttle and station is that you can actually build large distributed systems in space that are too big to be launched on any possible heavy lift booster, in fact, any booster you can imagine. And humans and machines working together can do this. They can assemble large, complex machines, and what's more, they can service, repair, and maintain complex systems too. And both the ISS and the Hubble Space Telescope missions demonstrated this. Now, if you apply this template to trans-LEO space, what you really need is the ability to get these people and machines to the points where these satellite assets are. And almost all of them are in orbits above LEO. They're in middle Earth orbit for the GPS constellation. They're in geosynchronous orbit. They're at the L points for scientific satellites. They're in highly elliptical orbits for certain strategic assets. So if you develop the resources of the moon, you can create a system to reach any point in cislunar space. So what are we trying to do? Well, I contend that the goal of space should be to expand our reach to cislunar and beyond. And by reach, what I mean is the ability to get this capability of people and machines to any point in cislunar, because that's where they're needed. That's where they're needed to build these big distributed systems. The way you do that, I contend, is you go to the moon and you learn to use those resources in material and energy that are on that planet to create this new capability. So, how can we do this? Well, in the last few years, we've learned quite a bit about the poles. We found out that it's a very unique microenvironment at the lunar poles. It's very unlike the rest of the moon. It's a zone where there's near perpetual sunlight and perpetual darkness. There is extreme cold next to fairly benign, reasonably simple thermal environments that receives oblique sunlight. That means that fundamentally you have these cold traps proximate to areas where you have near constant solar illumination. The cold traps contain volatiles. We now know that. We know that it varies widely in concentration and form. We don't know in detail what form it occurs, but we know that it's present in quantity. At a minimum, it's present in certain areas at the 5 to 10 weight percent level, possibly up to the 90 to 95% weight level in certain isolated localities. So when you go through all the various forms and possibilities, there are at least several billion tons of water at each pole. Some of it's highly concentrated, some of it's more widely distributed. So, given that boundary condition, how could you use those resources to create new capabilities? Well, what you want to do is you want to create an architecture where you can return to the moon using small incremental steps, but they all work together. So they're small, incremental, and cumulative. So with time, after each mission, you basically get a little more capability. And fortunately, because the moon's close, it's the only target in the solar system where we can actually do near real-time telerobotics and operate machines on the moon directly from control on the Earth. So what we tried to do, and by we, I mean my collaborator Tony Lavoie from Marshall and I, came up with an architecture that tried to describe how we could build this kind of a system to build this kind of capability. And we had some ground rules. One ground rule was that we must fit under the estimated budget runout that the Augustine Commission used in 2009. Now that's actually more money than NASA gets now. But you got to start somewhere. You got to pick some value just so you can get a rough order of magnitude costing exercise through this, and that was the boundary condition we picked. Because if you'll remember, Augustine concluded that what we proposed was not possible. And one of the things that drove us was to prove that they were wrong, and I believe they're wrong, and I still believe they're wrong. One thing that we did make that was different than the previous incarnation of Lunar Return was schedule as a free variable. We make constant, steady progress, but there are guidelines, there are not deadlines. So, what did we come up with? This is the reference. I'm happy to send anyone who wants this a reprint. It's on my website. But fundamentally, the first thing we did was to define our mission. And our mission was to create a permanent human-tended outpost to harvest the water and make propellant. We build it with these robotic steps, small incremental missions that work together on the moon and are remotely controlled from the Earth. So a lot of the pre-outpost emplacement, preparation, and demonstration of extraction of resources is done before the first human ever arrives. You use existing launch vehicles and a heavy lift vehicle if it becomes available. We wanted to be launch vehicle agnostic. So these things are packaged in 5 to 10 metric ton chunks, which means that you can launch most of our missions on an Atlas 551. And in fact, that's our launch vehicle of choice. The later missions use a 70 metric ton heavy lift vehicle. That was based on what the shuttle side mount could do. The cost and schedule had to fit under the existing runout budget, which means a cap of under $7 billion a year. And remember, since schedule is a free variable, we take as much time as we need. So we run it out for 16 years Our aggregate cost was $88 billion. But fundamentally, what that gets you is an outpost that can produce 150 metric tons of water per year. Now, the significance of that number is that is the point at which we move beyond break even. At 150 metric tons of water per year, we can send 2 human expeditions to the moon for roughly 4 weeks, twice a year. And after that point, any water we make, that's an annoying sound, any water we make is surplus and can be available for export to cislunar space. So what you do is basically create a permanent spacefaring system that's fueled by lunar-produced water. I've kind of summarized this in 2 slides. The initial steps, you basically put communication satellites in orbit that not only provide constant comm to all areas of the poles, but also provide a rudimentary lunar GPS system as well. We land 2 polar rovers at both poles, so we prospect so we can pick the best site. Basically, we high grade the sites by picking it from the remote sensing data first, then landing the rovers to do detailed characterization. We land an ISRU demo that basically proves that you can extract water from icy regolith. Then we land digger and hauler rovers, water tankers, electrolysis units. All of these are separate robotic spacecraft that are all basically a metric ton or less. But on the moon, they can all be hooked together and work together. There are solar arrays that track the sun where these rovers plug in and recharge their batteries every now and then. So effectively, we land near permanent sunlight and mine in the darkness that's nearby. So all of this supporting equipment basically gets us up onto production levels. And finally, we have 2 space-based assets, fuel depots, 2 of them in low Earth orbit and 1 of them in low lunar orbit. I've got sort of a conceptual cartoon that shows how this might all work together. All of this equipment has been placed by unmanned spacecraft before the human arrival. Human arrival occurs on the 16th mission, and by that time there is a habitat and a pre-in-place outpost and a waiting fuel tanker to refuel their lunar lander when they get there. So what do we get for this amount of money? Effectively, you create a system that can access the lunar surface on a routine basis. And if you can do that, you can access any other point in cislunar space. So by going to the moon and doing this, what we have done is create the system that I described earlier, where you can routinely access all the assets of cislunar with people and machines to do whatever job you want to do. So effectively, by adopting a paradigm of small incremental cumulative steps, you build the system over time. You don't basically do one-off missions for PR splashes. So effectively, you're creating wealth. You're not consuming it. You're building a system that actually generates the ability to go not only to cislunar space, but also to the planets as well. So I can imagine in the future 2 kinds of space programs. And Augustine used the phrase a spectacular series of space firsts, which to me basically kind of spells flags and footprints forever. We need to have a bread and circuses program where we can go and do a big PR stunt and then immediately cancel the program and throw away the capability we just developed. Instead, you might want to think about developing a program that builds a permanent infrastructure that does it in small steps that are all affordable. It can fit under any budget envelope. If you have low amounts of money available, you just go slower. If you have more money available, you go faster. But effectively, you're creating a permanent infrastructure. You're building a transcontinental railroad for space. So, why do we want to do this? I think the quote from Kraft Erica gives exactly the rationale that we need. If you want to become spacefaring, you have to learn to use what you find to create the capability. I think this is the way to do it. Now, I don't claim this is the only path to space bliss, but it is a path, and it's a path that I think deserves more intense study. And thank you for your attention. I'll answer any questions you got.
All right. Paul, it was smiles all around here at NLSI Central. That was just beautiful, beautiful. It's I think that sometimes all of us get so caught up in the weeds. You know, the volatile discovery was just one of the most important discoveries ever, of course, and was and is fascinating scientifically. But you have shown that it's a true game changer in terms of our entire path forward as a spacefaring species. And I hope you might have been able to share this with some of your friends and your words, I believe, yesterday. So up on the hill.
I did, as a matter of fact.
Yeah. So just fantastic, just fantastic. Loved it. So let's see if Ricky, could we scroll that just a little bit? I'm not getting. We have a couple of questions. I suspect that we might get a fair number more. Okay, so the first one's from Pam Clark. The newly discovered families of low delta V trajectories, weak stability boundary, low energy transfer, allow transfer from GTO or GEO with very little fuel expenditure in return for a bit more time, potentially increasing payload capability and reducing cost by quite a bit, particularly if standardized spacecraft buses are used. Please comment on how this affects your thinking about getting to the moon.
It helps it. I mean, effectively, we're agnostic on how you get to the moon. We have requirements for mass delivered and equipment delivered in a certain order, and whether we take 3 days or 3 months to get there is secondary. Because remember, the initial parts of the architecture are robotic, and so initially, in any event, we can take as long as we need to get to the moon. So certainly, having low energy, low cost trajectories helps us out a lot because we can increase the mass landed on the moon per mission.
Okay, great, thanks. Next question from Entu Varatharajan at PRL in India. The human influence contamination is going to pollute our natural satellite. Will this be going to impact the nature of the moon and its connection to Earth?
If you had large-scale industrial activity on the moon, that might impact the moon's environment, and it might upset certain scientific observations. Like, for instance, if you wanted to understand the lunar exosphere, I would try to do that as best I could before large-scale human arrival. But certainly, it's not going to affect the global environment of the moon. It's only going to affect the environment locally around the area that you're harvesting the water, and that's a very minuscule area compared to the area of the moon.
Great. Next one is from Michael Poston at Georgia Tech. I can definitely see the applications for human spaceflight. Do you see any uses for robotic missions, such as Planetary Science Division missions to the outer solar system?
If you want to look at, in terms of refueling transfer stages, absolutely. In fact, our intention in developing this was to develop a system that could harvest enough water to export excess water to cislunar space for use by anyone. We could sell it. You can imagine other government agencies as customers. You can imagine other nations as customers. You could imagine the science division of NASA as a customer if it wanted to send a big, very heavy probe to the Jupiter system. We could refuel it with LOX hydrogen at one of the L points, and it would be ready to go. It would be a great place to fill a departure stage. So yes, it impacts any space program you can imagine.
Okay, thanks. And the next one is from Larry Pianazek. What is the mix between robotic and teleoperated missions initially and in the final state?
Well, initially, they're all robotic, all teleoperated from the Earth, and gradually, as more and more people are going to the moon, we envision their primary aim will be to make the complete end-to-end system work, and they will do what is necessary. It might involve replacing some assets. It might involve changing out subsystems. It might involve just replacing entire systems if they need to be. So it's fundamentally, in the early stages, it's robotic on the moon. The people are doing the development and testing of the CEV and their launch vehicle. When people get to the moon, it's a mixture of people and machines.
Okay, great. Okay, and then Bob Thompson has a couple of questions. First is, what is the synergy with Golden Spike? And the second is, which pole has the higher net science rationale?
We haven't really thought about interacting with what the implications are for Golden Spike. I don't think their architecture is mature enough to determine if we have any impact with them or not. Right now, we don't know which pole is the most attractive for development. That's why we send a rover to each one. So the idea is to send a polar rover to the north and the south, the best sites we can identify, and then pick our outpost site on the basis of that data. Okay, great.
Then Larry Pianazek actually has a correction to his question. He says that he meant autonomous, the difference between autonomous robotic versus teleoperated. How is that? Could you comment on that balance?
It depends on what task you're doing. There's not much that we can totally automate. Certain repetitive, simple tasks, once they've been demonstrated, you can probably automate them. But in terms of the actual exploration and day-to-day operation of a robotic village, if I can use that term, on the moon, I think you want to maintain a high degree of human